Okay, hi. So yeah, welcome to the Polynomials class. Um, uh, I guess last Polynomials class by Atul, you all did some stuff, and I think I'll like kind of carry on from there. It's going to be a slightly more advanced lecture than the one Atul took. So hopefully we'll solve some good problems. So let's start with the problem. I'll just share the statement. Okay, so let's start with this problem. Is the problem statement visible? Okay, so can you guys please like try to do this problem for a while? Also, if you guys have any questions, like just unmute yourselves and ask. I'll probably not be keeping up with the chat. Also, feel free to mention any like ideas you have about the problem. So maybe let's give like 5 to 7 minutes to have some idea about the problem, and then I'll maybe start with the solution. So did you guys do finite differences last class? I actually forgot to check.
No.
Okay. You guys did Lagrange interpolation, right?
Yes.
Okay, cool.
Is it monic or monoic?
Oh, I think that's a typo. It's supposed to be monic. It's a typo from Mayops, I think. Leading coefficient 1. Does anyone have any ideas about how to approach the problem? Okay, so I think I'll like start probably with the solution. Like it is quite a hard problem at face, but like it's very hard to actually give hints towards the problem without completely spoiling it. And I also like wanted to choose this problem because uh, the key lemma it uses, it's basically really useful and it comes up a lot. So first of all, know that when we are like, whoops, so I just clicked on something I was supposed to. Okay, yeah. So suppose you are trying to solve the equation, let's say just p of x is at most m for some real m. So first of all, try to think about the problem in this way. Like the phrasing for this is kind of weird because like you know that whenever you were trying to solve p of y is say mod of p of y is less than m for where say y is any real, right? So when you're trying to solve an equation of the form of this, you know that it's going to be of the form of something like this, mod y less than, let's say, a for some real a. Why is this true? Because like otherwise, if y was unbounded sort of, then you would run into problems because the polynomial p is like non-constant, right? So if you had like a lot of like an unbounded if the solutions to this equation were unbounded, then you would like run into problems because when like say if p has, let's say, a positive leading coefficient, then as y would grow large, p of y would grow large and its absolute value would be greater than m. So we know that like whenever you're trying to solve p of y absolute value less than m, you would have solutions of the form mod y less than a. So we basically kind of need to ensure that uh, you have like you can choose the degree smartly such that like uh, x mod q of x less than a has at most like degree d solutions. So the idea for this problem is basically also the another statement that we know about this is that q of x is. So the fact that p of 0 equals to 0 was given in the problem statement, that's like kind of superfluous. It's like completely unnecessary. I'm not exactly sure why they gave it in the problem. Whatever. So like we'll like try to build upon this. So the idea is basically we will use Lagrange interpolation with like any where like suppose the degree of q of x is like say d, then the idea is that we will use Lagrange interpolation, right, on like any d plus 1, I think on any d plus 1 integers, and we will try to bound stuff. So what do I mean by bounding stuff? We'll like see. So suppose like you use Lagrange interpolation on the points x0, x1, x2 up till like xd, right? So you can say something like q of x is summation of I equals 0 to d f of xi multiplication j not equals I, x minus xj, xi minus xj, right? So now one thing that we are going to try to exploit is that the only information basically that we know about q, and that is q is a monic polynomial. So from this expression, what is the okay? So from this expression, what's the leading coefficient?
Sum of f of xi by product xi minus xj.
Yeah, that is correct. Yeah. So like if you try to write the uh, oops, leading coefficient for this, it turns out that the leading coefficient is something like summation I equals 0 to d. I mean, okay, I was meant to write q of xi here. Q of xi multiplication j. And by the problem statement, it is equal to 1. So what we are going to try to do is like we are going to try to bound this somehow. So like if this idea like feels very vague, I can sympathize with you, because I can't think of a way like you're actually supposed to motivate this without knowing the lemma itself, because the problem is kind of like meant in a way like after I finish with the lemma is kind of well known and it's going to be used in a lot of places. So after I finish with the lemma, you'll just see how the problem unfolds after that. But this is actually a very common technique in Lagrange interpolation to like uh, do a bounding kind of stuff with after you get the expression like this. So now the idea is to bound this. So bounding like the bounding is like going to work something like, so LHS you can like say is something like, okay, so yeah, LHS is at equal to, at least you will take the max term out of this. So
It will be less than equal to, right? Because
oh,
max.
oh yeah, sorry. Oh. So this now, can you suggest a way to bound this term?
D by 2 factorial.
Yeah, that is one way. So can you like think of another way such that the summation becomes nice? Like you'd have difficulty. I guess that would probably work as well using some techniques, but there's actually a much easier way to do it. So the I'll not spend a lot of time behind this. So basically the idea is that, so suppose this value is just, let's say, a, capital A, right? So a times, you can just bound it by something like this, by d factorial times n minus d. Okay, I'm stupid. I switched to dn. Okay. Like I factorial times d minus I factorial, right? So why write it like this is basically like when you take n factorial here and n factorial here, this basically becomes n choose I. So this becomes like a times 2 to the d d factorial, right? So now you know something like 1 is at most a times 2 to the d by d factorial, or other words, a is at least d factorial times 2 to the d, right? So what does this thing tell you? Like, we started with a monic polynomial q, we interpolated it at any d plus 1 integer points, and we found that the maximum value of the polynomial at d plus 1 is at least d factorial by 2 to the power d, right? So this is like true for any monic polynomial, and this is basically the lemma I was talking about. So this is like incredibly important to keep in mind this. And so now think about this. So now we wanted to prove that. Page. Okay. So we wanted to prove. So we wanted to solve equations of the form like u of x at most a, right? And we wanted that this equation has at most d solutions where d is the degree of q, right? So now so the idea is basically from this equation you understand that whenever you choose d plus 1 integers, you will have some of them gives a q value greater than this. So the idea is simple from here. So you basically choose a d such that this thing is like also note that this thing can get incredibly small because 2 to the power d obviously grows a lot larger than d factorial, right? Or large enough d. So you can just take a d such that this holds.
Wait, a de factorial grows larger.
Yeah.
Wait, did I just blunder?
No, it's fine. Like right hand side becomes too big, but left hand side is fixed. So it's a contradiction.
1 second. Oh yeah, sorry. Oh yeah. Okay, that was stupid. But yeah, as Atul said, like this is constant, so it will grow big, too big sometime. So basically, the idea is like you can choose a d such that d factorial by 2 to the power d is less than mod a. And so now, whenever we need to solve for q of x is like at most mod a, we know that every solution, integer solution x to it, must like satisfy uh, like okay. So now suppose like if we are trying to solve for like if you are like now trying to solve for something like this, now we know that if you, so from the previous statement, like if you have like d plus 1 integers, one of them gives a very like sort of high enough value. So this kind of tells you that if suppose so if there were d plus 1 integers, one of them would be greater than this, right? So basically this just works. So does that make sense? Like choosing such a d works.
Can you show the statement once?
Oh yeah, sure. Oh wait, I just wrote the infinity to other way as well. Okay, this is bad. So I'll just repeat what I said towards the end because I kind of like confused myself because I wrote the inequality the other way around. So you just like choose d such that this thing is like greater than mod a. So what that guarantees is like whenever you have something like mod qx is less than mod a, then you like suppose a was here minus it, let's say, and this was the factorial by 2d, and this was minus the factorial by 2d, right? So sorry. Yeah, and suppose like so having this would require q of x to be less than d factorial by 2 to the power d, right? And you just observe that there are at most d integers that can do that. So, and now like since yeah, this should just finish the problem. Is the solution clear?
I still don't get the last part, like from the second page.
Okay, so from the lemma, we observed that whenever you have d plus one positive integers, uh, you interpolate them at like any interpolate q at any d plus one, not positive, just any integers, then you would have like one of them has a q of x value greater than d factorial by 2d, right? So the idea is basically, now suppose, so what did we want to like achieve? Sort of we wanted like q of mod q of x less than mod a to have at most d degree q solutions, right? Right. So what we are going to do is like suppose, so now think sort of like think about this. So suppose this was your interval minus a and a, right? And you chose d factorial by 2d such that this was greater than, like the mod value is greater than a basically, right? So what this tells you is basically whenever you have q of x less than mod a, you also have q of x uh, less than d factorial by 2d. Does this make sense? And from the previous lemma, you know that there are at most d solutions to this, d integer solutions to this.
Oh, okay.
Okay, yeah, so that is the idea. Yeah, I messed up the conditions. And also like you can, if like this function is kind of increasing, I think. And so like if you have if you just increase the degree, so that works out as well. Um, okay, so does anyone have any other queries on this problem? So I wanted to basically show the idea of how bounding works well with Lagrange interpolation, because it's like a very important idea and comes up in a lot. So any questions regarding this? If not, I'll just move on to the next part. I think I'll just talk about finite differences of it. Okay, so let's start with finite differences. 1 second. So I'll just talk about finite differences and then solve them. So finite differences is like, suppose you have a polynomial f of x, right? So we say that the first order forward finite difference of f of x is uh, just f of x plus 1 minus f of x. All right. So, and we can like do something like the second order finite difference of f of x to be something like del of f of x plus 1 minus del of f of x. So this comes out to be f of x plus 2 minus 2 times f of x plus 1 plus 1 f of x. So, and like we can define f of like rth finite difference, forward finite difference of f of x. So now one thing which is very noticeable is like the degree decreases by at least 1, right, for every finite difference. So like del of f of x will have, suppose the degree of f of x was n, the del of f of x will have degree n equals to 1, n minus 1, sorry, n minus 1, right? I mean, at most n minus 1, because if you don't have that, no, it will have degree n minus 1, sorry. So something like if you have, let's say, x to the power n was your polynomial, when you do like x plus 1 to the power n minus x to the power n, you can see like x to the power n, x to the power n just cancels out. So yeah, that is the thing. So what does, so one thing that tells you is like the nth finite difference is actually a constant, and the n plus 1th finite difference is 0. So these are actually important things. So first of all, we like try to find a general formula for finite differences using like this. So I'll just write out the formula. proven by induction basically, and we'll like look at some important properties sort of. So we observe that this was equal to f of x plus 2 minus 2 f of x plus 1. So like by so basically the uh, theorem I'm sort of like trying to look at is, yeah. So we can write del k f of x as, so this is the kind of formula I think. Okay, I forget it every time. So yeah, so this is the formula I was talking about. So this holds. So this is a general formula for the kth order finite difference. You can like sort of prove it by induction, I guess. So this is not like very important. So the most important case is like when k is equal to n plus 1. So this is like the most important case, which actually like tells you something about the polynomial. And what it says is something like, so this is actually quite important. The fact that this very nice looking identity holds, right? So this is one of the more important properties sort of. And another property you should kind of know is like, suppose del k p of 0 is suppose ck, then you have yeah, p of x equals to summation k is 0 ck, etc. So this was like the sort of theory you're supposed to know about finite differences. Is the like the part clear? Uh, any doubts regarding what I said? I mean, this is probably your most like sort of important formula. Also, like another thing one can easily see is like, suppose f of x is monic, right? Then what is with degree n? What is this the nth finite difference? I said it was going to be a constant. So how it works is like, suppose you have, so the answer is basically n factorial for this. How it works is something like, if you have like x to the power n plus stuff I don't really care about. So you basically you are doing like x plus 1 to the power n minus, so like this is for the first finite difference, let's say, right? So suppose this is I'll just repeat what I said. So suppose you are like calculating the first finite difference, right? And then there is something like, this is x plus 1 to the power n plus stuff that is degree less than or equal to n minus 1 minus x to the power n plus stuff that is degree less than equal to n minus 1. So you really care about, so by binomial or something, you have something like n choose 1 x to the power n minus 1 minus x to the power n plus stuff I don't care about. So as you can also, the n minus 1 stuff cancels out. So you see that the x to the power, so this polynomial has like a degree of n minus 1, right? And the leading coefficient for this is n. So similarly, when you do the second order for finite difference for this, you will have an n minus 1 term coming with the n which is already present, right? And when you like repeat this process, it gives you like n factorial for the nth finite difference, which is a constant. And if p of x has like a leading coefficient, say c, then you just have a c to the power n term with the n factorial. So that's about it with regards to finite differences. Uh, does anyone have any questions regarding what I said? Not, I'll just like standard problem.
No, it's fine.
Yeah, and just a second. Uh, yeah, so this is the problem. So yeah, please try it for maybe 5 minutes, and yeah, the hint is obviously use finite differences. It's not a very hard problem, I think, but I think this gives a good idea about how you can use finite differences. So when is the class supposed to end?
10:45.
Okay. Has anyone seen the problem before? I actually plan to do some probably multivariable polynomial stuff after this. We'll see.
So it like P1 divides m plus 1th finite difference of P evaluated at 1, m plus 1 or m, 1 second.
P of how does it work? M plus one finite difference is a constant. Wait, what is your degree of P? Let's say the
Degree is
degree.
different, right? That is degree P. Yeah, D. Okay.
Yeah, M is like not something. So suppose like degree is N for working purposes. So I like kind of get done with the problem quickly. So like this problem basically very quickly falls apart after you like use this idea. Ah, no. So when you like basically do the n+1 at finite difference. So first of all, like the problem statement, like will obviously proceed by contradiction. So if the problem statement were false, like you would have something like P1 divides, P2 divides, and up till like, let's say P of up till 3m+1, I think. Yeah, up till P of 3m+1, right?
N+1.
3n+1, yeah.
Oh yeah, sorry. Yeah. Right. So the idea is we will like try to make use of the identity uh, of the like the k+1 at finite difference is 0, right? And we will take it modulo p of k for some good k, which we will figure out. So like first of all, realize that we will eventually hit a different number in this sequence of 3n+1 values, right? Because they all can't be the same value, of course. So suppose you have like p of k is something that is not equal to, by different value I mean like modulus, right? So something like you can't like go on having 5 divides minus 5 divides 5 divides minus 5 and so on and so on and so on. You will eventually hit a different value with modulus different than 5, like a 15, let's say. So does that make sense?
Yeah.
Okay.
Yes.
So does anyone have a question? Okay, I'll just proceed. So suppose p of k is such that mod of p of k is not equal to p of 1, and p of k minus 1 is mod of p of k minus 1 is equal to p of 1. In other words, it's like the first different modulus different term in the sequence. So the idea is like we are going to use the k+1 at finite difference formula as I just mentioned, right? So uh, uh, so the k+1 at finite difference formula tells you something like, okay, I'll just use I here. So we are going to try to make a lot of use of this formula, right? And like we are also going to take the values out of mod k, right? So now mod p of k. So like what is the like, do we know any information about k? Like can we have some bounds about k?
Yeah, like k will be less than or equal to 2 times degree of p.
+1, I think.
Yeah, +1, +1.
Yeah, because 1 is different. Yeah. So basically what the idea is like, since see like, so something like the equation p of x equals to plus or minus p of 1 has how many solutions? 2n, right? So the value of k cannot actually grow larger than 2 of n+1, and also like up till 2. So why this is nice is basically because it also tells you k+1 k plus n is at most 3n+1, right? And that is also kind of why the problem works, right? Like, so now you can choose x such that you have a k plus n term here, right? Which is at most 3n+1 by how we are solving the problem, basically using that. So what is our choice of k for this equation? Like, how do you choose k? So sorry, x. How do you choose x? Like, remember one thing, like we do not know any information about p of 3n+2, right? Whatever we know is up till p of 3n+1, and we also know that uh, uh, k plus n is at most 3n+1, which is kind of why the problem works. So basically the idea is like, if you took x equals to n, which is like, might seem like the first case, you would run into problems because you're not n, sorry, k. If you chose x equals to k, which might sound like a good choice at first, you will run into problems because you can't basically work with p of k of n plus 1, which is a term that will come up if you choose x equals to k here. So we'll basically choose x equals to k plus 1, sorry, k minus 1. So when you like write this out, sort of, right, so what you will get is like p of uh, p of k plus n is equal to p of u minus 1, I think, to the power something, plus stuff divisible by p of n. Do you agree with this statement? Again, like recall, since we had k plus n is at most 3n plus 1, right, we can like very easily write something like p of k, sorry, p of k divides p of k plus 1 divides p of k plus 2, and so on. Does this make sense up till p of k plus n, right? So now when you like use the finite difference formula, right, so you basically get like p of k plus n is equal to minus 1 to the power something p of u minus, basically plus or minus p of u minus 1. Sorry, I meant
Yeah, p of
p
k
of
minus 1 and stuff divisible by p of k.
p of k and stuff divisible by p of k. Yeah, right. So like when you take this equation mod pk, right, what does this give you? You know that this is 0 mod pk, and this is equal to plus or minus p of 1 mod pk, right? But that cannot happen because p of 1 is strict, well, basically because this holds, right? We concluded that p of 1 divides p of k, and they have different magnitudes, so p of k has a larger magnitude than p of 1. Does this make sense? So this basically tells you that uh, the so basically what the assumption was, the assumption we started with was p of 1 divides p of 2 divides up till p of 3n plus 1, and that assumption is false, so contradiction. Does that make sense, like the proof?
Yeah.
Okay, anyone has any questions? I'll quickly pull up the other problem. For some reason the text it doesn't work on this. So I'll like start working with like give a problem on multivariate polynomials, but it's really not like quote unquote multivariate. It's basically more of like just understanding how to factor and stuff. So some ideas regarding multivariate polynomials are like, so some ideas that I've found are work useful with multivariate polynomials are like view them as functions of uh, one variable, generally like works very well. So like something like you can just view something like p of x1 x2 as f of x, like x2 constant or something, and see how that goes, right? So this is a very important idea, I think. And other than that, like just keeping stuff factored is a good idea, I guess. Like something like if p of x comma x comma other values I don't really care about is equal to 0, this basically tells you that x1 minus x2 divides p of x1 x2, the n-variate polynomial. So these are some properties sort of that are kind of useful, but it really boils down to your problem solving skills and like how well you understand like factoring and stuff. So I'll like just start with a problem. Just a second. Okay, in front of one, yes. We're supposed to put 2004. 2004. Okay, now just a second. Yeah, so can you guys please try this problem? Is a problem, yeah. So the problem statement is visible, right?
Yeah.
Okay, yeah. Please try this problem for a while.
Is
Maybe
this Aryan?
It's Russia, I think.
Okay, okay.
yeah, this is Russia 2004. So some stuff I also wanted to kind of say about Lagrange interpolation, but I really couldn't find very instructive problems on them. I'll try to give some of them in the problem set. Is something like often you use Lagrange interpolation like intentionally for, say, you have an n degree polynomial, you intentionally use Lagrange interpolation on like a on like n plus 2 points, such that the resulting polynomial you get has the x to the n plus 1 coefficient 0. So that is an idea that is like I've seen it getting used in some places, probably useful to know. So for example, a hint that can get used in 2019 A5, ISL 2019 A5, I think that is a pretty good idea. I can't really think of more problems based on it, so decided to like, skip that part. So like one thing about the problem is it doesn't really matter a lot about r of x comma y. So what's really important in the problem is like q of x minus q of y divides p of x minus p of y. So that is literally the meat of the problem, sort of, and you have to like try to understand how to incorporate that in whatever techniques you use. I'll actually be gone for a minute and we can like we can go through. Does anyone have any like ideas to begin, like how to try to solve the problem? I understand like 5 minutes is obviously too low to even get a feel for the problem, but well,
Can't you just do like Euclidean division and
come again.
like you do Euclidean division again and again?
So something like set b equals to aq plus b for a and b polynomials and see how that goes. That is one
We
approach,
can
I guess.
induct on the degree, maybe.
Very good idea. Uh, that is a very good idea. Uh,
Maybe assume P0 equal to Q0 equal to 0. Then we'll get Px divides Qx. But I don't think we can recover the final condition with that.
We'll get the position that Px divides Px, not Px divides Px.
that is fine. Yeah, the degree idea is definitely a very interesting idea. I actually like, I plan to actually show a solution using like more divisibility ideas more than like degree stuff. But here's one way to proceed with the degree idea, like degree induction idea. So like, suppose I think off the top of my head, if you like consider saw some kind of a solution in Ops that goes like this. So suppose you have so suppose you do so suppose okay, suppose degree of p is like, let's say, m, and degree of q is, let's say, n, right? Then you can I think do something like, suppose omega to the power n is 1, right, is a primitive nth root of unity. Then I think look at something like how p of omega x minus p of x behaves, like how this behaves. Like basically look at the assertion where you put x equals to omega x and y equals to omega y. I remember seeing a solution on AOPS which went along these lines, and the degree induction is successful. Like this, this should probably give you like oops, n divides m. Oops. Did the screen just go blank?
Yes,
Ah,
it's back now.
but everything is blue for some reason, like the background and stuff.
I think this is a Monte problem.
Come
For
again?
us, it's fine.
Monte problem.
I'll just stop sharing and share back. Just give me like a minute. Yeah, is the screen visible?
Yeah.
What is it? Did I break the mid? Okay, okay, my laptop is glitching for some reason.
I can't see the screen.
Okay. Is the screen visible now? Didn't really change anything. Is the
It's
screen
visible to me.
Same.
I'll just, I think I'll just rejoin, like just leave the meeting and rejoin.
Yeah, the screen is visible. Was visible at least.
Oh yeah, I stopped sharing. Just a second. Ouch. Did I just leave the file? Yeah, there we go. Yeah, I'll just share. Yeah. Now the screen is visible, I think.
Yes.
Yeah, I don't know what really happened. Gadgets are weird. Yeah, so this is one idea. Like, I'll suggest you try. I mean, yeah, this is a working idea for sure. Like, I'm kind of interested in showing another solution, which is more like along divisibility lines, really. So first of all, we will try to explicitly like think of a polynomial s that works. So the way we do it is using like Lagrange interpolation, right? So suppose we assume like m was degree f. So suppose m is something that is a huge like integer which is greater than degree f, right? And we interpolate. So now we like interpolate a polynomial at values of at like m+1 values, sort of like how we do it is basically we want the polynomial to satisfy s of q of x equals to well, it's not f, it's p of x in the long run, right? So we basically uh, do it something like let's say we pick integers such that we pick not integers, reals x0 x1 up till xm, such that let's say g of I'm working with q. So suppose q of xi is bi and p of xi is ai, right? So we will interpolate in such a way such that s of bi is equal to ai for all I up till m. So does this make sense? So we will build a new polynomial. Ah, just a second. Uh, Hello.
Hello.
Yeah, sorry, I think I got disconnected once again. I'll just share. Okay. Let me share it. Yeah, so we'll just a second. Yeah, so we'll build a polynomial s of x such that s of q of x equals to p of x in the long run. So the way we do it is we like pretty explicitly interpolate it at like a large number of points. Large is something like larger than degree of p of x, right? So we know that this uniquely determines a polynomial s of x with degree at most m, right? So now, as I was talking about in the previous
Damn.
my internet is really glitching.
Oh,
I'll just work with it for 2 minutes, 2 more minutes, I guess. If it doesn't work, I'll have to. Okay, so this uniquely determines s of x with degree at most m, right? So
You are
yeah,
no
so
longer sharing screen.
oh,
Like, is there some event for stopping sharing?
come again. Yeah, I'm sharing now. Can you see the screen now?
Yes. Now your
Damn,
video is paused.
am I still sharing?
Yes, yes, yes. That is it.
I mean, it's kind of hard to understand because like the screen just went blank all of a sudden in front of me once again. Okay, so like suppose degree my degree is at most m, right? So like the idea is like you will
I guess
in
you would have set it some keybind for stopping sharing. That's what is happening again.
come again.
Like I'm saying, you would have by mistake set some event for stopping sharing. That is what is happening again.
Oh, I'm not so sure. I don't think so. I'll just figure it out, I guess.
Okay.
Just a second. Just a second. Yeah.
Maybe you can just do it today by turning off video because your internet isn't working. Isn't it?
I think there's a problem with my computer. Hello. I'll actually like try to leave and rejoin, I think, because I'll just like restart my computer and rejoin. Like, how do I even leave without ending the meeting?
There should be a button.
Make someone the host, I guess.
Make Ruthar the host.
Yeah.
Okay, I'll just shit. I forgot to unmute myself. Am I audible?
Yeah. Can
Okay,
you
okay.
make me the co-host?
Yeah. really sorry about the disturbances. Okay, so is the screen visible?
Yeah.
Yeah. Okay. So like we got to the point like we were trying to like explicitly sort of determine a polynomial like such that uh, like which would equal for which s of q of x would equal to p of x in the long run, right? So now what we do is like, as I said during the sort of motivation talk, like how to deal with multivariate polynomials, we like sort of fix a value of y and we will try to see how the divisibility relation works out for like one variable not as a variable, for like one of the variables constant, one of the variable stays a variable. So you know that if you of this is true, right? So we know this, right? So now we will like use y equals to xi, right? So q of xi divides p of x minus p of xi. So this is something that is true by the problem statement, but we also know something like q of x minus q of xi is divisible by s of q of x minus s of q of xi. Right. Why is this true? This is because for any polynomial f a minus b divides f of a minus f of b. So yeah, does that make sense?
Yeah.
Okay. So what is s of q of x of y? This is basically just p of x of y, right? So now when you like combine the two divisibility statements, they basically tell you q of x minus q of xi is equal to p of sorry divides s of q of x minus of p of x, right? So this is true. So now one thing you know is like yeah, so for how many values of xi is this is true? So this is true for like m plus one values or just m values of xi's, right? Where m is like very large. But also note that since okay, so now like we can, if the q of xi's were like different, right? Like so every q of xi is a constant term, right? So now if these constant terms were like different, we could have like a lot of factors for this polynomial s of q of x minus p of x, and this is something we actually want in the long run, right? Because we sort of want this polynomial to have more factors than its own degree, which would basically mean it's a zero polynomial. So one way to do this is like we want q of xi to be different. But well, I mean, this is kind of like very easy because if you couldn't choose a lot of xi such that q of xi were different, this would just mean like q of xi is basically a constant polynomial, which would also force p of x to be a constant polynomial. Which would also force p of x to be a constant polynomial. So such this is easy to choose, else constant. So what does this tell you basically? So from this, we understand that multiplication of I equals to 0 to m, q of x minus q of xi divides s of q of x minus p of x. But as I said, like eventually, like for large enough m, degree of LHS is just greater than degree of RHS, which forces uh, s of q of x equals p of x. So does the solution for this problem make sense? That is the solution. So this is basically exploiting the divisibility condition repeatedly. Does anyone have any questions?
Deba is asking in chat to summarize the thing.
Okay,
Like the
so yeah. So first of all, we are basically going to think of the problem as a, so someone had said it was possible to do an induction solution like induct on degree, so that is perfectly true, but I was like more interested in showing this solution, which I think is kind of instructive maybe. So like the main idea is like, first of all, we will build a polynomial s of q of x, which we want, S of x, such that we want it to be equal to, such that we want S of Q of x to be equal to P of x in the long run. So how we do it is like we interpolate basically it at a lot of values, because we don't know its degree for sure for now. So like we interpolate it at a lot of values, right? So we choose a lot of xi such that S of Q of xi equals to P of xi, right? So that would give us a value of so that would give us a value of S of x, and that is a unique polynomial, right? So now from there on, we will use like different the division relations. So we know that Q of x minus Q of y divides P of x minus P of y. So this is true from the uh, like the problem statement. And you also know that, so now what we do is like we choose y to be xi. So this is like a very important tactic sort of in multivariate problems, where you like choose a specific value of one variable to get good results. And so now I know you also know that Q of x minus Q of xi divides this thing, right? So basically Q of x minus Q of xi divides S of Q of x minus P of x. So now the idea is like, if Q was a non-constant polynomial, we could choose Q of xi is to be a lot of different things, right? And if like, now Q of xi is like a constant value at the end of the day. So like suppose you had like a lot of m plus 1 Q of xi's, right? Each of them different. So each of these factors is a different factor, right? So this means like now S of Q of x minus P of x is a fixed degree, let's say n, right? I don't know about it. But what I do know is like I can choose a lot of xi's such that the factors of the LHS will eventually have degree greater than n. But this only happens when S of Q of x equals to P of x. So basically this is what we want. Like we can choose a lot of xi's such that this whole, so the divisibility relation basically holds, and at some point the LHS degree oversees like the RHS degree, which would force the problem statement. Yeah, what was asked before. So does that make sense?
Why would the degree of LHS be a lot larger than the degree of the RHS?
I mean, like
The
if you,
degree of the LHS here should be, if the degree of Q of x is n, then the degree of the LHS should be m plus 1 into n, and the degree of the RHS should be m into n.
yes. So like it should get larger for like value, like for a high value of n, right? I don't
Yeah,
know.
but then it's not like you
Oh,
on one hand you have mn, and on the other hand you have
oh, you
mn
just have a
plus m.
problem with. Acha, okay.
Yeah.
I mean, if n was large, then kind of still holds, but okay, that's not really good thing. Okay, so the next, I think I'll just talk a bit about differentiation, which is like I'll just like prove a theorem, which is like called the Nash-Sauter's theorem. So differentiation is basically a very important tactic, and it is like really important like when we are dealing with repeated roots, sort of like, because it's like well known, like if R is a repeated root of f of x, then f and f dash share the same root R, right? So the next theorem is this is, I've just talked a bit about it. The proof for this, I really love the proof for this theorem. So let a comma b comma c be polynomials with complex coefficients such that a plus b equals to c, and they do not share any common factors. Prove that max degree a, degree b, degree c is at most degree rad abc minus 1. So what is rad abc? Rad abc basically, so like rad of any polynomial f of x is like largest square tree divisor of f of x. So how that works is something like, if you have like, for example, if you have something like f of x equals to x minus 2 whole square times x minus 3, the rad is just x minus 2 times x minus 3. So does the definition of rad make sense? I guess it's also like very widely used in number theory. So I'll prove this theorem. I think it's a really nice theorem actually. Like the proof is really nice because it's has ideas that get used a lot. So yeah, so I just move on to the next page. Does everyone understand what the statement is trying to say? Like, I guess it's like you can't have a lot of like new loop sort of. I guess I like move on to the proof. So like so the main idea of the proof is like we will continuously use a relation of the following form. So like, for example, you saw something here, right? So like, if we consider the value, if we consider the polynomial f divided by rad of f, if f was square free itself, it's just a constant polynomial, right? And if f was not square free, then it divides f, right? And if f like, and not only does it divide f, it also divides f dash, as a matter of fact, because like, yeah, it just a second. Yeah, it divides f and f dash. You can like just figure it out using like normal differentiations. And so this is something that we will use a lot. So how we like really use is like, so suppose like you have so something like c equals to a plus b. So when you differentiate it, you get c dash equals a dash plus b dash, right? So we will actually try to extract the identity from these two equations. How we do that is something like this. Suppose you have like try to double count sort of c dash, right? So you can write it as c times a dash plus b dash, and you can also write it like this, right? So this is going to give you bc dash minus b dash c equals to ac dash minus ca dash. So the main idea of the proof is like, we'll prove that if the condition is like false, like so obviously we're proceeding by contradiction. So the main idea is like, we'll try to show that this obviously note that like these values are like non-zero, right? So we will like try to look at the factors of this polynomial ac dash minus ca dash, and we will basically prefer that a lot of stuff divides this polynomial, and by a lot of stuff I mean like stuff which is higher degree than ac dash minus ca dash. So that is basically the main idea of the proof. Like, if the problem were to be fake, then if the theorem were to be fake, that would not happen. And also note that ac dash minus ca dash is not equal to 0, and that is because if it were equal to 0, you would have something like ac dash equals to ca dash, which means like a divides ca dash, but you know that these two do not have any common factors, so this would just mean a divides a dash, which cannot happen because degree higher, right? Degree of a is just higher than a dash. So yeah, so this is what we will try to prove. So by the previous lemma, we sort of understood that f by rad f divides f and f dash, and so it divides any linear combination of them as well. So using this, we can write something like, so suppose you want to focus on bc dash minus b dash c. Yeah. So we can write something like c by rad c divides bc dash minus b dash c. You can also write b by rad b divides bc dash minus b dash c because of the same reason, and a by rad a divides this thing, that is ac dash minus ca dash, which is also basically equal to bc dash minus b dash, right? So is this up till here clear to everyone, like whatever we have done till now for this proof?
Yes.
I'll proceed, I guess then. So like, so now note that since ABC were all co-prime, all these factors are co-prime as well, right? So this basically means that ABC by rad of A times rad of B times rad of is divides BC dash minus B dash. But what is the denominator actually? These are co-prime factors. These are co-prime polynomials, right? So you can just like, the rad of all of them is just the rad of ABC. So like, try to understand why this works. So think about like, I guess, numbers. Like if you have something like 10 is equals to 2 cross 5, right? And if you have something like 17 just 51 is just 3 times 17, right? So these are co-prime numbers. So hence the rad of 10 times rad of 17 is just the rad of 170. So that is how it kind of works. So this is BC dash minus B dash G. And we will prove that we actually have a degree problem here. What I mean by a degree problem is we will prove that degree of ABC is degree of ABC by rad ABC is actually greater than BC dash minus CB dash, which will give rise to a problem. So what happens is like degree of ABC by rad of ABC is degree ABC minus degree dash. So we could, like, if the theorem were false, then we could just assume that this is, let's say, greater than A, right? I mean, when you not greater, I think more like this. Yeah, it's did I just mess up the signs? Okay, yeah, sorry. This is greater than A, and this is obviously greater than CB dash minus BC dash. So because of the degree bounding thing, so BC dash minus CB dash must be 0, which is a contradiction. So does this make sense?
Yes.
So I'll just recap the proof once again. So like we started with this full identity BC dash minus CB dash equals AC dash minus CA dash, and we understood that none of them could be 0, and then we basically looked at its factors of the form like CY dash C and so on. So this is actually very common idea, sort of like you have to use this kind of like divisibility and like forcing degree problems while dealing with multivariate polynomial divisibility generally. Not, I mean, yeah, it kind of comes up a lot. So the next problem, I think probably run out of time. I'll just see if I can do this problem. So 1 second. Just give me a second. Is it okay if I like maybe take 5 to 10 minutes more after lecture time? Just like sort of make up for the time that is lost. Are there any differences in here? Okay, I'll just pull up for the problem. Okay, yeah, so this is a problem. So suppose f and g are polynomials with complex coefficients such that degree f and degree g have GCD of 1. Suppose p and q are polynomials with complex coefficients in x and y, like bivariate polynomials, such that p of x plus f of x plus g of y. So yeah, actually just a second, I'll just do the easier version of this problem. I was like, I think looking at the harder version. Yeah, I'll just 1 second. So suppose m comma n are like or relatively co-prime integers. Prove that x to the power m minus y to the power n is like irreducible in CF. So what this basically means that if x to the power m minus y to the power n equals f of x comma y times g of x comma y for some bivariate polynomials f and g with complex coefficients, one of them is a constant. So does the problem make sense?
Yeah.
So maybe there's actually no time. I'll actually like start with the solution for this because like so the idea for the proof is like, once again, what I was talking about, like we'll like sort of like substitute values smartly once again, right? So also, like after we do this problem, feel free to try the previous version of the problem. So this problem is Elmo SL 2012 A5, and the previous problem which I like deleted was A7. So do actually maybe try the A7 after we are done with this problem. So how we do this is something like, okay, so suppose you had x to the power m minus y to the power n equals to f of x comma y times g of x comma y, right? So first of all, notice that one easy way to get 0 on this side, so that is going to tell us about like the roots of f of x comma y and g of x comma y, is like just put something like t to the power n comma t to the power m. Why is that? Like basically because t to the power n to the power m, so basically because of this identity, right? So when you plug x equals to t to the power n and y equals to t to the power m, you get something like f of t to the power n comma t to the power m equals to 0, or g of t to the power n comma t to the power m equals to 0, right? And this happens for all t, right? That is true. So now this also means like this is like this thing holds for infinitely many t. So one of these relations holds for infinitely many t. So like one of by sort of infinities and whole unity. So one of above holds for infinitely many. And if something holds for infinitely many t, you just know that it is 0, because polynomials are really well behaved and you can't have like a lot of roots. Infinitely many, of course not. So suppose f of t to the power n times t to the comma t to the power m is equals to 0 for all t, right? So now can you think of a logical substitution for t which would actually tell me more information about the polynomial? Also keep in mind that we have the very nice relationship m comma n has GCD1.
Roots of
Any,
unity maybe.
yeah, that is the idea basically. So what we are going to do is like we are going to basically plug t equals to like e to the power 2 pi ik by m, which is like mth root of unity. So when we do that, now also note that m is relatively prime to n. So when like when you look at the set kn, right, where k comma m is 1, so this is like eventually you are going to get like all the primitive roots of unity. Not just primitive, I think you're just going to get all roots of unity, like when you look at the set k equals to n, and where like k runs from 0 to m minus 1. So that is, so this basically tells you like when you substitute like omega into the relation, which is a very powerful relation, you basically get f of omega to the k comma 1 equals to 0 for all k basically, because of the residue thingy here. Does this make sense of how for why we can say like this relationship holds for like all
Yes.
k epsilon? So this is because like kn is eventually going to take all residues mod n, right? So now think about it. F of x comma 1 is a polynomial in x, right? And we also understand that it has like and it has roots at omega power k, right? So it has at least m different roots. So this basically means the degree of the x degree of x comma y is at least m. But similarly, you know that degree, the y degree of f of x comma y. What I mean by x degree is basically when you view f of x comma y just as a polynomial in x and view y as constant coefficients, right? Then what is the degree of the polynomial? But wait, like we had something like f of x comma y times g of x comma y is equal to a polynomial where x degree is m and y degree is n, right? So this basically forces g of x comma y to have the x degree like equal to 0 and the y degree as well equal to 0. It just basically means constant. So does that make sense? I kind of rushed over the proof, but I hope the details are clear.
Yes.
So this is actually a very like useful thing to keep in mind, like useful substitutions and using roots of unity in this kind of situations. Maybe one problem I can let you guys try, and that is or actually yeah, that should be fine. I was thinking if I have any other problems. So this problem is like in similar spirit to the ones discussed. Suppose you have polynomials p and q with complex coefficients, right? And suppose you define r of x comma y equals p of x q of y minus p of y q of x. Prove that r of x comma y is square free. So maybe I'll let you guys try this problem. It's like not very. I think I should have just like probably put it in the problem set. I actually forget about this problem. I'll just like talk about one more problem first. So one thing I actually wanted to talk about was like how polynomials grow, sort of like growth rates. So by growth rates, I mean like any polynomial will eventually, like suppose you have p of x equals to adx power d plus stuff I don't care about, then I mean obviously like suppose if ad is positive, then eventually this is going to be the term that dominates everything else, right? And so you can basically, for large enough x, you have a relation like and so basically you can say something like it gets sort of squashed between two like two x to the power d stuff. And also some other useful stuff to know is like p of like any polynomial grows slower than exponential. Exponentials are eventually like going to take over. Okay, so one problem which is like kind of a funny problem I want to show. Okay, the question is, do there okay, yeah, do there exist infinitely many points xi comma yi such that for all sequences bi of reals there exists a polynomial p of xy with real coefficients such that p of xi comma yi. So does this problem make sense? So basically it tells you like, does there exist infinitely many points xi comma yi such that whenever you take any sequence bi, there will be some real coefficient polynomial interpolating those points at xi comma yi. So what do you think the answer to this is, given what we just discussed?
No, I guess.
Yeah, the answer is actually no, but unsurprisingly, because like the basic idea is like you can take bi's to be anything quite literally. So if you take them to be something like exponentials, right? Something you have like e to the power I times layers. So if you have something like e to the power let's say zi, where zi is like very larger than xi and yi, right? Then in those cases you would have a problem, and that problem arises basically because you can sort of bound the polynomial, even if it's a two-variate polynomial. Suppose it was something like cmn x to the power m y to the power n, right? You can just take max of CMN mod sort of like something like this. And basically work with that. And this is again like at most, let's say a mod of, when we are working with xi and yi, it would be something like max of xi to the max of xi comma yi to the power m plus n, and that kind of that's like how the bound works out, because you would have something like p of xi is something like you'll get something like this, maybe it's max of xi comma yi whole to the power degree, right? Which can obviously keep up with exponential sequences. So is the idea of this problem here? It is kind of a stupid problem, but I still wanted to show it for because it kind of highlights how like size ideas sort of work, because I think it's okay problem for understanding growth rates. So does anyone have any questions with the problem and how the bounding works out?
No.
Yeah, I think I'm already over time. I'll just like quickly go over the solution to this problem, because like it's not like very hard also, like and that was also the last problem I really wanted to do, so I probably just take 5 minutes more. Okay, so for example, for this problem, the technique is a lot similar to like what we had done for the Mason's-Slaughter's theorem. So for first, obviously you assume that there is a polynomial p of x comma y such that the square divides r of x comma y, right? So this tells you two things. That is like first of all, obviously p of x comma y divides p of x p of y minus p of y p of x. Oh, sorry, I forgot to mention one condition, that is they have no common factors. P comma q have, I'll be leaving the AOP statements of the problem, the AOP links of the problems, or sources wherever applicable. So this is obviously very essential, otherwise you would not be able to solve the problem. So assume that this holds, right? Then you can write something like p of x comma y divides p of x p of y minus p of y p of x, right? So now when you take the x derivative or say the y derivative, the divisibility relation still holds because of the repeated roots thing, right? So we can also write p of x comma y divides p dash x p of y minus py q dash x. Does this make sense why like the second divisibility relation is true? This is really the meat of the problem.
Yes.
So from here on, you can basically do like rinse and repeat what we did. So you can probably multiply this with I think p of p dash x and this with p of x. So that should give you, I think, p of x comma y divides p of y minus p dash x qx minus px q dash x. I like just writing in short. So from these two, you get like this relation holds, right? So now, so assume that this is non-zero, right? Because I mean, otherwise you'd run into the similar problems like we had in the earlier case. This has to be non-zero, right? Because otherwise you'd have p divides p dash. So now one thing we understand is, right, t of x comma y is a factor of p of y, right, for like a suitable choice of x such that such that this factor sort of like works out suitable x, but and like viewing y as a constant, viewing x as a constant again. So and similarly, you also know that p of x comma y is a factor of q of y, using the same techniques like in this one. Does this make sense? So this cannot happen, right? This is because you now have P of y and Q of y have a common factor. Does that make sense? So like we assume that this term was non-zero, right? Then we have something like P of x comma y divides P of y as a polynomial in y for suitable x, and similarly it's also a factor of Q of y, but we know that P of x and Q of x have no prime factors. Sorry, one have no prime factors at all in common, so this like cannot hold true. So you basically have something like p dash x q of x equals to px q of q dash x, and when you like just integrate it sort of you basically get something like ln of p of x equals to ln of c times q of x, which basically tells you something like p of x equals to c times q of x, which is again a contradiction because they cannot share any factors at all. So does the proof make sense? I had to rush over it because we are out of time already. Does anyone have any questions regarding the proof of this problem and in general, any problem from the lecture? Feel free to ask.
Did you integrate for the ln thing?
Yeah, like yeah.
Okay, okay.
Like this is just integrate. I'll probably be uploading the problem set by tomorrow.
What if you had t of x comma y almost purely as a polynomial in x, where there's no y term at all? Couldn't you have t of x comma y dividing p dash x q of x plus minus p of x q dash x?
Yeah, once.
Then can't we take the derivative with respect to y?
I think like yeah, I think then just yeah, that should work out. Like it will have at least like one of the like one non-zero coefficient. Like it can, I mean, it will have one term in either x and y. Then you can just take the other derivative.
Okay, cool. Thanks.
Okay, so that's all about the talks. I guess I'll leave. Thank you all for attending.
Thank you for the class.
Thank you. Bye.
Thank you. Bye.